So in this class, let us see the applications of the first law of thermodynamics. So first we will see the specific heat of gases, and then we will, the second half of the lecture, we will concentrate on the state of an adiabatic process. So equation of state for an adiabatic process. So let us see first the specific heat of gases. So specific heat of gases. So here gases means unless stated ideal gases. So this is molar specific heat. So we will talk about molar specific heat of gases. So with molar specific heat of gases, we mean the amount of energy given to a unit mole of an ideal gas so that its temperature rises by unit degree centigrade. So this is what we mean by specific heat of a gas. Now, when we give heat to a gas, then the gas temperature also increases and the gas performs some work. So the same energy is utilized, a portion of the energy is utilized in increasing its internal energy, and another portion is utilized in doing the work. So how a gas will respond to the heat input will be different for different processes, and thus a gas can have different values of specific heat that depends upon the process. So let us see first what we mean by specific heat of an ideal gas. So molar specific heat of an ideal gas is that amount of heat that is required to raise the temperature of a unit mole by unit Kelvin temperature. This is what we mean by the molar specific heat. So 1 by C will be 1 by N dQ by dt. This is what we mean by molar specific heat. Now let us see that why this specific heat has so many different values for a gas. So when heat is given to a ideal gas system, then that heat is utilized in increasing its internal energy as well as doing work. So it depends on the process that what proportion of heat energy will be used in internal energy or work done. So we see thus the molar specific heat of an ideal gas depends on the process. So thus there can be infinite types of processes possible. So a specific heat of an ideal gas can have also infinite values. So now let us see some basic process, very popular processes. So this is the PV diagram, and suppose a gas is carried through a process called isochoric. So this is isochoric process, and let us see, when PV plot is a straight line like this, A to B, then it is isobaric process. So when we talk about this process, if the gas goes through this process, we say the specific heat as CV, and for isobaric we have the term Cp. So now we define molar specific heat at constant volume as, so we define molar specific heat at constant volume as CV, as CV is equal to 1 by N dQ by dt oblique V. So when I say oblique V, that means V is constant. So V is equal to constant, we write. Again, so this is molar specific heat at constant volume, CV. Also, we define molar specific heat at constant pressure as Cp is equal to 1 by N dQ by dt at constant pressure. So these are the standard notions we will use. CV to denote specific heat at constant volume, and molar specific heat at constant pressure as Cp. So you see here, can we guess now that whether Cp will be more or Cv? So when we supply heat in isochoric process, then there is no work done. 100% of heat is used up in increasing. So important point, in isochoric process, 100% of heat given is used for increasing the temperature, whereas in isobaric process, a fraction of heat is used to increase the temperature. So to increase the temperature in this process, you require more energy. That means Cp is more than Cv. Thus we can say, Cp is greater than Cv. How much greater? We will see later on. So Cp is here greater than Cv. So now let us see what is the possible range of specific heat of an ideal gas. So range, important, very important point. The range of molar specific heat of a gas. So this is we want to, so let us predict what could be the possibility. Suppose I am giving 4 options for this. So number 1 option C, this specific heat C is from 0 to infinity. Number 2 option I am giving is C is from 0 to Cp. Number 3 option I am giving is C is from Cv to Cp. And the 4th option is from minus infinity C to plus infinity. So you see, molar specific heat of a gas is actually from minus infinity to plus infinity. That means specific heat of an ideal gas can have any value from minus infinity to plus infinity. So because it depends on process how the gas is going to utilize the heat input. Now you see, we are comfortable with this term that when we supply heat energy, the temperature will rise. So you see, C is equal to 1 by N dQ by dt. So when dQ is positive, that means we are giving heat, dt is positive, so C is positive, clear. But what about this negative point, that C can have negative values? Negative value means you give heat to a system and the temperature decreases. This is what we mean by the negative specific heat of an ideal gas. So now let us see when we can have a negative heat of an ideal gas. So now let us see, this is our mathematical form of the first law. Delta Q is equal to delta U plus delta W. Now suppose I have delta Q, I am writing delta Q here, and this is delta U here and delta W. So now if I give heat 100 joule of heat inside, then depending on how much it is using in delta U and how much it is using in delta W, we will get different values of specific heat. So one thing is that it is 60 and 40. So you see, you give 60 and 40. Next, another possibility is that you give 40 and 60. Then it is 70 and 30. So there are many combinations possible. So in all these processes, you see delta U is positive. So the specific heat in all these processes is positive. But other possibilities are also there. Suppose this is 100 and this is minus 10. Suppose this is 110. That means we have given heat into the system, but since work done by gas is 110 joule, so internal energy change is minus 10. Although we have given heat into the system, but the temperature has come down. So for this process, the specific heat is negative. This is 100 minus 50. This is 150. Summation is this. So you see, this is the first law. This plus this must be equal to this. So again 100 minus 100, it is 200. So you see, for all the three processes below, the specific heat is negative, and for upper processes specific heat is positive. So you see, whenever the gas does more work than what energy it gets, in that cases delta U becomes negative, and so delta U becomes negative, so temperature is related with the change in internal energy, delta T becomes negative and C becomes negative. So thus for an ideal gas, we can have minus infinity to plus infinity as the specific molar specific heat. So now let us see the internal energy of an ideal gas. So you see here, this is the PV diagram. For an ideal gas, we use PV diagram to discuss the equation of state and all properties. So from kinetic theory of gas, we know that the internal energy is a function of temperature, because temperature is directly related with the average kinetic energy of molecules, and according to kinetic theory, the molecules does not possess any energy other than kinetic energy. So there is no potential energy. So whatever energy the gas has, internal energy, that is because of its kinetic energy of molecules. So it is directly related with temperature. So if temperature is constant, there is no change in internal energy. So suppose this is a process isotherm of temperature T1, and this is another isotherm of temperature T2. So we have two isotherms of temperature T1 and T2. So all the points on this will have a internal energy U1 and all the points on this curve will have the internal energy U2. This is valid only for an ideal gas. For other gas, other type of systems, the internal energy may not be function of temperature only. It may depend on V also. So, but for an ideal gas, since internal energy is a function of temperature according to kinetic theory. So, you see, if I move from here to here isochorically, you see I am moving isochorically. So, this is the isochoric process. So, if let us calculate delta U. So, in this case delta U, U2 minus U1, the internal energy of this by this, and this will be equal to, since this volume is constant, so the change in internal energy will be given by, you see, delta Q is equal to delta U plus delta W. So, this quantity is 0 for this process. So, delta U will be equal to delta Q. So, only for this process. So, only for this process we have this term delta work equal to 0. Now, you see delta U is equal to delta Q, which is NCV dt for this process. That means you have delta U as NCV dt for this process. Now, you take a general point called A and you take a general point B, and if I move from here to here, I will get the same change in delta U, because all the points here has the same U1 and all the points have the same U2, and I know that the difference from this isochoric process, that this is equal to this. Thus the change in internal energy for an ideal gas is equal to NCV dt for any process. So, for any process, that delta U is same. So, it is for even if the process is isobaric, this is equal to NCV delta, because delta U is the same for ideal gas for any two isotherms. So, if this value we have calculated NCV dt, this is the same for any process. So, very important point, that delta U is NCV dt not only for isochoric process but for all processes it is the same.